Thank you for the opportunity. We're super excited to be presenting about Habana processors in this forum. I'm Sree Ganesan. I'm responsible for AI software product management at Habana Labs. And with me is Steve Thorne, who leads our sales. So in this presentation, we will basically cover the Habana Gaudi processor, very high level view of the architecture. We'll talk about our cloud and data center solutions powered by Gaudi. We'll talk about our software and support processes for developers, and then wrap up with a summary. And I'll have hopefully plenty of time for questions. So this slide is the backdrop for the founding of Habana in some sense. So if you look at this, it shows how the ML training compute doubles every 3.4 months. There is a significant growth in the complexity and size of models. There is the requiring frequent retraining of models. And these two kind of also add to increased costs. So all of this is ending up in terms of indications of challenges for innovation and growth for those who are pursuing AI training. So it makes it a right time in terms of putting forth dedicated AI processors to address compute, memory, and communication challenges specific to this domain. And in this backdrop is where Habana is founded in 2016 to develop purpose-built deep learning training accelerators and deep learning inference accelerators. So we launched our first inference processor in 2018, followed by our training processor in 2019. And in late 2019, we were acquired by Intel. And since then, we've been operating as an independent company within Intel. Today, we are fully integrated with Intel and are leveraging the full scale and resources and infrastructure within Intel, and more importantly, the ecosystem and customer partnerships. So like I said, there are two key focus areas we had, Gaudi for training and Goya for inference. And today I will be talking about Gaudi, our training solution. So this is a picture of our Gaudi card, and it's a industry standard form factor, the OCP OEM form factor. This is one of the key tenets you will see across this presentation, is that we have, as a guiding principle for the design, adopted standard interfaces, standard protocols, standard form factors, and tried to keep as much of the proprietary and vendor-specific information and capabilities very, very limited, so that it allows the ecosystem to thrive with whatever our offering is. So Gaudi, like I said, purpose-built for training in the data center. The key focus areas: cost efficiency, flexibility, because it's a new architecture, it's a new solution for training. We wanted to make sure that it was designed to ease model migration from whatever solution you had before, whatever hardware architecture you were using, to the new Gaudi architecture. So there's a lot of focus on the software stack and making sure that it was easy to program in the ML frameworks. And obviously, for training, scalability is a very critical aspect, and both the hardware and software are architected with scalability in mind. So this picture shows a high-level view of Gaudi architecture. It is a heterogeneous architecture with fully programmable tensor processing cores. We refer to them as TPCs. We have a configurable matrix math engine, and we have DMA engines. And in terms of memory hierarchy, we have 32 gigs of HBM, we have shared SRAM and local memory in each TPC. The unique feature of Gaudi is the integration of 10 100 gigabit Ethernet ports on die, and this is used for multi-chip scale-out training. And the combination, and this is all in 16 nanometer technology. So when you look at the efficiency, it comes not from the process node, but it's actually from the architecture that you see the benefits in terms of the efficiency that Gaudi provides. So we talked about the second tenet, the flexible and easy model migration. First principle was ease of use. We wanted to make sure it was integrated with TensorFlow and PyTorch, the most popular frameworks we have, with very minimal code changes to get started. Synapse AI, which is our software stack, maps the model topology onto Gaudi devices. At the end of the day, developers enjoy the same level of abstraction that they are accustomed to today and can leverage the goodness and the value proposition of Gaudi. Second is customization. There are always these special class of developers who want to customize models and extract the best performance from this architecture. The Synapse AI software stack has a TPC SDK, which facilitates development of custom kernels, so you can actually program those kernels to the TPCs and squeeze every last ounce of performance that you're interested in doing. And then we have balanced compute and memory. There's the fact that we have 32 gigs of HBM is very similar to GPU. So the effort in terms of porting models over from GPU to Gaudi becomes a little simpler, and that eases the whole migration story. Then the third factor we talked about was the scaling efficiency. This is our industry's first. We have native integration of 100 gigabit Ethernet ports onto every Gaudi. There are 10 ports. This eliminates network bottlenecks. And I talked about the use of standard interfaces. This is using standard Ethernet both inside a server and across nodes. What this allows you to do is use the same scaling technology within the server, across servers, to build a rack and build a pod. And it allows you to eliminate lock-in with any proprietary interface. These are popular data center interfaces, and so we're just leveraging whatever is popular in the data center. And by integrating it on die, we've obviously allowed the system vendors to reduce the total system cost and power, and because there are fewer discrete components being used, and all of these savings are passed on to our customers and our end users. So this is a sample of our integrated server. It shows 8 Gaudi OCP OAM cards, and each of them, like I said, has 10 ports of Ethernet integrated on die. So they are connected in an all-to-all non-blocking fashion so if every Gaudi is communicating to 7 other Gaudis, and the remaining 3 ports are used for scaling out outside of that node. And then the separate PCIe ports are used for communicating with the host CPUs. And this server is something that we will talk about in terms of an offering that we have available currently. So I'm going to kind of take that server and then say, okay, how do I build a scale solution, whether it's a rack level solution or a pod level solution? It's fairly straightforward, depending on your needs, both in terms of the workload, in terms of how many systems you would need. You identify the number of servers you would want. It's easy to put together a rack based on the rack power limit. You would identify the number of servers in that rack, and then you hook it up with standard Ethernet cables, standard copper cables, and an Ethernet switch. And then you can then keep hooking up multiple switches and build out your pod and keep scaling this very easily and build out a large training cluster. Because the intent is to keep it very, very simple to build a scale-out solution. So I want to then shift focus to our cloud-based solution, and this is our EC2 AI training instances. These are coming very soon, and Andy Jassy at reInvent 2020 went on stage to say that these new EC2 instances will leverage 8 Gaudi accelerators, and they will deliver up to 40% better price performance than the current GPU-based instances that are available for deep learning training. These are Amazon's first non-GPU instances, and this whole idea behind the improved cost efficiency makes AI training more accessible to many, many more customers and democratizes AI for a large set of users who are interested in applying AI in many, many scenarios. So these Gaudi-based instances will benefit from a full stack of EC2 services. We will have the DLAMI and DLCs for Gaudi. We will have integration with SageMaker. We will have ECS and EKS for orchestration with containerized applications and efficient scaling across multiple Gaudi-based EC2 instances with ENA and EFA. Now on the on-premise solution, we'll talk about the server that we have available. So we are partnering with Supermicro, and we have two solutions available. We'll talk about Gaudi first. We have the X12 Gaudi training system, which is a very similar design that I had shared a few minutes ago. 8 Gaudi OEM cards with 2 Ice Lake CPUs, and then this is a picture of that training system. We also have a similar inference solution called Super Server that has 8 Gaudi Goya PCIe cards and a dual socket Xeon as well. So these Gaudi and Goya systems have been used to power San Diego Supercomputer's Voyager research program. If you've not heard the news, it's in July we announced the Voyager program with San Diego Supercomputer, and this goes into service sometime in the fall of this year. It's funded by an NSF grant, and we are working with AI researchers to identify various deep learning application, models and in astronomy, climate sciences, chemistry, particle physics, molecular biology. There are very many areas where we're exploring where we can leverage deep learning training in these science and engineering domains. So this is a little bit on the hardware side now, but obviously the story doesn't end with the hardware. We have to enable the software solution. We have to have also a very easy onboarding and engagement with the developer community. And I'm going to talk a little bit about our software stack and also about the resources in terms of what we have for our developers for just how you can get access to a lot of the content and how you can get support. This is a very simplified view of Synapse AI software suite. Like I said, it's integrated with TensorFlow and PyTorch. And the goal is to enable deep learning training on Gaudi with very minimal code changes. So we have a framework integration layer that attaches to TensorFlow and PyTorch. And then under the hood, we have our graph compiler, communication libraries, we have a rich kernel library. All of these pieces are working in cohesion to enable optimal mapping of the neural network topology that is captured in the framework computation graph and then mapped over to Gaudi. And like I said, we have a lot of developer resources available, reference model, kernel libraries, software downloads, documentation, all of this is publicly available. And we have the TPC SDK that advanced users can start leveraging to write their own custom software kernels. So I'm going to do a little bit of a double click on each of these to add some color to each of those components. So the topmost layer is our framework bridges, and these basically attach to the TensorFlow and PyTorch frameworks. We do not make large changes in the framework itself. Our intent is to be able to take an officially released version of the framework, and then our library would then be used to interface with the framework itself. And so this is where we want to preserve whatever capabilities are available in TensorFlow and PyTorch and allow the developers to continue to work in that ecosystem and in those frameworks, while Synapse AI does all of the translation and mapping and optimization under the hood. The core component is our graph compiler and runtime that generates the optimized binary code and implements the model topology on Gaudi. Now, we talked about all of the scaling benefits of Gaudi and the fact that we have integrated NIC ports on Gaudi, and our communication library is called the Habana communication library. And we have two flavors, HCL and HCCL, which is a port of HCL, which is NCCL compatible. So it allows the efficient implementation of scale up between the different Gaudi cards inside of a single node and scaling out across multiple nodes for distributed training. And if you use HCL, you can use the Gaudi integrated NICs for scaling within the single node and across nodes. And there are certain users who would like to use host NIC-based scale out, and we allow them to do that with Pickle-based libraries. On the left, you will see that we have two types of kernel libraries. I talked about Habana's rich kernel library. We have a wide variety of operations that are supported, performance optimized for Gaudi, and the graph compiler automatically identifies the right set of operations and to pick the right set of kernels and leverages those for generating the binary code for Gaudi. Now, the TPC programming tools allow you to then register these custom kernel libraries. So for the TPC side, we have a C-based language. It still has a few more intrinsics, which we are now calling TPCC. So it has a C compiler, LLVM compiler, a simulator, debugger. You can use those independently to develop your kernels. And then we have ways to then customize the ops in the framework. So you register the op in the framework, you have a kernel that you've developed for it, and then you can basically allow Synapse AI to then take that op you created in the framework, find the right kernel that you created, attach it as part of the customer kernel libraries, and then start leveraging those during your execution. At the lowest part of the stack, you have the HLML and the management and monitoring libraries. This is very similar to the other management and monitoring tools you would have found. This is for firmware updates and for kind of looking at the status of the different cards and understanding what's going on in terms of the actual hardware and querying the hardware. This slide, I'm going to talk a little bit about how TensorFlow is integrated with Synapse AI, just to show you how we kind of map from the TensorFlow framework graph into Synapse AI. So Synapse AI receives a computational graph of the model from the framework, and then it identifies subgraphs that can be accelerated by Gaudi. So those are the blue nodes that we have coverage for those operators, and our bridge identifies these and then kind of encapsulates them as nodes that can be run on Gaudi. And the rest of the nodes that we do not have coverage for on Gaudi, we can get, those are, the yellow nodes, and those will execute on the CPU. So this then kind of, this encapsulated node is then handed off to the graph compiler in runtime, which will then generate the optimized code and execute and run it on Gaudi. So what this allows you to do is not have to worry, and under the hood, basically, this is how Synapse is trying to do the mapping from the computation graph in the framework into the Synapse AI graph. We talked about making it easy for porting models over from existing hardware that you're targeting to Gaudi. So I wanted to provide a very simple example of how easy it would be to get started with Gaudi. So this is a very, very simple example of an MNIST model. So you'll see the two lines of code that I've highlighted. We need to load those two, basically load the Habana, import the Habana module, and then load that Habana module. And this is all that you need to get started with targeting Gaudi as the device that you want to start offloading work to. So Gaudi is referred to as the HPU, or the Habana processing unit, in the TensorFlow framework and PyTorch frameworks when you register them. So once it's loaded, the HPU device is then prioritized over the CPU. So if an op is available that you can run on either the CPU or on HPU, that op gets assigned over to the HPU and then gets executed on the HPU. It gets actually, it goes back into building that graph and then doing the graph level optimizations, and then it gets mapped to the HPU. If it is not supported on the HPU, it just falls back on the CPU. So what the intent was that if you have operators that are not supported, if you have a model that you want to take over and run it on Gaudi, at the start, you do these two lines of code, you end up with something functional that you can get up and running quickly. That said, this is only a necessary but not sufficient set of changes that are required. This gets you started. Then you have to go do the analysis of where are the bottlenecks, which are the operators that are running on the CPU versus the HPU. If there's a lot of back and forth communication, that's going to lower your performance, and then you start analyzing the bottlenecks for performance and then looking at how you optimize it. So we have debugging tools We have a profiling tool, a trace analyzer tool. All of these tools are available for you to then start, identifying how you can optimize these models and get better performance from your model on Gaudi. So obviously this is just the guts of the software stack and the changes that are required to get started. What we've also done is spent a lot of effort in making it very accessible to our end users and developers. So we've put together a lot of resources on our developer platform. So if you go to developer.habana.ai, all of the information that I'm sharing is available right now. So we have, if this is just the start page that you will land in. You have documentation, resources, and technical guides to get started. There's a community forum where you can get the latest software and where you can get the models. All of this you can then, and our models and performance data is available as well on this developer platform. So from the developer resources, you basically end up with, like I said, simple starting, how to start with Gaudi, how to migrate models over to Gaudi, how to write custom kernels, what do you need to do for debug and optimization, where are the Habana optimized models, and how you get started with updating your software and installing your software on the Gaudi systems.
Hey, Sree, can I interrupt real quick?
Yes.
There was a question from Ryan to the group about the Synapse AI graph compiler. And I thought it might be worthwhile to repeat it here so everyone hears it. Just curious to know, is the code for the Synapse AI graph compiler open sourced or closed sourced?
Right. So the Synapse AI stack is proprietary. All of the code is closed source, and eventually we will get there. At this point, it's all currently proprietary content.
Great, thanks. And at that point, you were showing some of the Habana developer tools. We post the graph compiler software binaries out to the tools, right?
Yes, I'm going to cover that.
Okay, I'm jumping ahead. Sorry.
Yes. So the next is our documentation page. We have a lot of our user guides. We've got API reference guides, TPC programming guides, a lot of information on also the supported operators in TensorFlow and PyTorch. The goal is for you to come in here as developers and be able to get an idea of a high-level overview of the software and hardware architecture, be able to start getting a feel for all of the different capabilities that are available, the features that are available, and how you can start using those. And this would be your go-to resource in terms of the user guides and API guides. And the developer documentation is fully web-based and searchable, so you can go in there and search for whatever content is available. Now, in terms of actually the downloading your software and installing, whether it's the container images or the firmware and the drivers, you would go to Habana's vaults. So on the developer page, you have links to all of the different components and the packages that you would need, the OS versions that it's supported for, and then you can go download those specific versions. We call this our vault, so you can actually go straight to the vault and get like the actual file, for each release, you can get the full set of components and navigate through that directory structure. It's vaults.habana.ai. And this is publicly available and accessible right now. I want to spend a few moments on our GitHub at github.com/HabanaAI. We have several resources which are again meant to make it easy for onboarding developers and users on Gaudi. We have our setup and installation, model references, our roadmap, our custom kernel examples. A lot of this is available. I will touch upon that in a second. So for software installation, that setup and install repository provides detailed instructions and a flowchart to walk through all of your scenarios and allow you to set up your environment with the Synapse AI software stack. We have Gaudi optimized Docker container images with all the necessary dependencies that are available and publicly available, released in the vault. We support TensorFlow and PyTorch. This stack is showing you TensorFlow container image, There's also a similar container image you'll find for PyTorch. And we also have capabilities for orchestration. We have support for enabling Kubernetes with our Gaudi plugin and a kubeflow MPI operator. And on that setup and install repository, if users want to build their own Docker images, we publish our Docker files, so you can go ahead and then build your own Docker images with those Docker files. Just a word on like the different frameworks that we support and the versions. So TensorFlow 2 is the what we support today. We have support for 2.5. We keep trying to stay up to date with the latest releases. And I believe we're on PyTorch 1.7 right now, and we're catching up to 1.8 very quickly. For Kubernetes, we are currently on the vanilla version of Kubernetes 1.19. We are working on adding support for Containerd. Right now, that's coming in one of the immediate, like the subsequent releases. We support Ubuntu 18.04 and 20.04. Docker is our container runtime, and for distributed training schemes on TensorFlow, we have Horobot, and we just introduced tfdistribute. On PyTorch, we have the native PyTorch distributed library. So this is sort of our quick view of what's available in terms of software installation and setup. In terms of the Gaudi reference models, we have a model roadmap that's published on GitHub, and then for every model that we have enabled and optimized on Gaudi, we have published all of the scripts and detailed instructions for the developers to go there and get those models and then be able to run them on Gaudi by just following those instructions. So you can go look at our model references repository and find like all the columns, all the models in the done section are published and available in our model references GitHub. So you can see that mostly we're focused at this point on vision and NLP models. It's a more like a strategic prioritization versus trying to have a much more broader range of domains. Over time, we will address additional domains. We're kind of at this point, I wouldn't claim that we have full coverage of all of the operators and all of the models. We are continuously improving our coverage of both the TensorFlow and PyTorch operators, and continually adding more coverage for more models. And we would love to get feedback from the community and the developers on models that they're interested in, so that we can start focusing on adding the optimizations in those in Synapse AI and enabling you to get the benefits of the cost performance benefits of Gaudi as early as possible. Last but not the least, we have the Habana Developer Forum. And here's where we want to actually encourage developer community to be active. We have lots of questions there and FAQs available. We, again, would like to encourage our developers to come in and post questions and ask. If there are any clarification questions or insights you would like to share, this would be a great place to engage. And we want it to be a vibrant community, and would love to invite you folks to be part of that community and watch what's happening on Habana as well. Last but not least, I know that this is targeted at a community for scientific research. There are a tremendous number of exciting opportunities in scientific research areas for deep learning training applications. And we are excited to have you explore these possibilities with our Gaudi training processor. And we're looking forward to engaging with this community and getting started with Gaudi in this domain. So I know I have 45 minutes, but we had a very short time to prepare this material. So I'm happy to answer questions if there are more questions.